Okay, great. Okay, then I guess we can start. So it's a pleasure to have here Alicia Lamarche from University of Utah, which is going to talk about what's written here, right categories, arithmetic and rationality.
Okay, thanks so much for the opportunity to talk and for coming to my talk. I really appreciate it. So what I'm going to talk about today is joint work with Matthew Ballard, Alex Duncan, and Patrick McFaddin. And I have their websites listed there. Usually what I do is these blue things are links, but I'm trying something new today. So if it goes terribly, I'm very sorry. Okay, so first of all, I want to give you sort of an outline of what I'm going to be talking about. First, I'm going to try to motivate the question that I'm looking at. Then I'm going to give a brief description of some of the machinery involved, and then I'll give you some more details about the results that we showed. And so this work is in 3 separate papers, mostly this first one that's joint with Matthew Ballard, Alex Duncan, and Patrick McFaddin. And the main result that I'm going to talk about today comes from something that hasn't been posted on the archive yet. That's joint work with Matthew Ballard. And just so that we're clear on like notation stuff, throughout the talk, X is going to be a smooth projective variety over an arbitrary field K. If I write K bar or KS or K sep, what I really mean is a choice of separable closure of K. When I write dB of X, I really mean the bounded derived category of coherent sheaves on X. And we'll say that X, a variety X over a field K has a rational point or a K rational point or a K point if there exists a map from spec of K to X. Okay, so I want to start off with a question. It is the following. Can the derived category be used to answer rationality questions about X? So I guess first what I want to do is be more specific about what I mean by rationality. Maybe this isn't necessary in this seminar, but if you do number theory, I don't know. I'm just trying to cover all the bases here. So I'll say that X is rational if it's birational. To projective n space over K for some n. So they're isomorphic outside of some lower dimensional stuff. Okay, so I have a question. Given 2 varieties X and Y, how do I know when they're birational to each other? So I don't do birational geometry, but one of the few things that I do know about birationality is weak factorization. So, okay, weak factorization says that if I have a birational map between X and Y, I can decompose this as a series of blowups or blowdowns along smooth subvarieties. Okay, so if I'm trying to come up with some sort of naive tool to detect birationality, there's 2 things that this tool must satisfy from a naive point of view. First of all, it better behave nicely with respect to projective space because that was literally in the definition of rational. So we want our tool to behave nicely with respect to Pn. And we also want it to play along well with weak factorization because that's one of the few things I know about birational geometry. Okay, so my claim is the following. Maybe the derived category is a tool that we can use to do these things. So, okay, first of all, does it behave nicely with respect to Pn? I think we all know the answer to that because we're in a seminar on derived categories. But Bailenson decomposition of Pn says that the derived category of Pn will decompose as just n twists of the structure sheaf. So that's pretty nice. And does it behave nicely with respect to weak factorization? I mean, I think it does. So I would say yes because of Bondel and Orlov's blow-up formula. For semi-orthogonal decompositions. Okay, so from this naive tool to detect rationality, I have a really vague idea, which I will make precise soon. So maybe if X is rational, this might imply that its derived category isn't too complicated. So maybe X is rational means that dB of X is nice. I'm being vague on purpose because what does it mean for the derived category to be nice? I mean, I have to be more specific about that. And on the other hand, I have another question or idea. Maybe if the derived category is nice, this means that X is rational. So that's what I want to look at today. And to convince you that this isn't some nonsense question, there are a few conjectures I want to talk about. So first of all, a conjecture I think that's due to Orlov says that a smooth projective variety, or asks if a smooth projective variety with a full exceptional collection is rational. And a conjecture due to Lentz says that over a general field K, if X or dB of X has a full K exceptional collection, this hopefully means that X admits a stratification into a locally closed stratification into K rational subvarieties. So okay. And so now is probably an appropriate time to mention that in the first paper that was listed, so it was joint work with Matt Ballard, Alex Duncan, myself, and Patrick McFaddin. We show that smooth projective varieties, smooth projective toric varieties. I sometimes forget that varieties aren't just toric varieties. So smooth projective toric varieties defined over field K with K points that have a full K exceptional collection are rational. So we show that in.
By rational here, you mean always rational over K?
Yes, I guess like K rational. So birational, the P and K. Okay, so in general though, like if I'm asking the question, like if the derived category is sufficiently nice, does this imply that X is rational? I have some evidence that like maybe yes in low dimension. So I want to take a look at that. So let's just start off with curves. So I guess we could organize this by genus. So for genus 0, these are Savary-Brouwer curves. These are only going to have full exceptional collections when they're trivial or like actually isomorphic to P1. So okay, so in genus 1 or bigger, bigger than or equal to 1, the answer is no.
Can I ask with your definition of toric, is every genus 0 curve is toric or only P1?
Yeah, so I'm not assuming anything with toric varieties here. I guess like the genus 0 guys should just be twists of P1, right?
Yeah, but you see, in your in the theorem, you have this toric varieties over non-closed fields, and so I suppose their torus is not necessarily the usual torus, but the twisted form of the torus. And yeah, so I suppose things like genus 0 curves will be like toric curves or something.
Right. Yeah. They'll be twists of P1. So for genus bigger than or equal to 1, Okawa showed in 2011 that these guys don't have non-trivial semi-orthogonal decompositions.
Sorry, is the definition of toric here such that if it's toric over the algebraic closure, then it's toric over the base field?
Yeah, I'll be more specific about that in the next section. But yes, yeah, it's just a K variety that base changes to a toric variety over the separable closure. Okay, dimension 2. So in 2016, we all showed that if I have a full K exceptional collection, and my variety is geometrically rational, this implies my variety is rational. And earlier in 2015, Brown and Shipman showed, at least over C, that if I have a full strong exceptional collection of line bundles, together with some stability conditions on these line bundles, then my variety is rational. So I could talk about dimension 3, but I don't really have any good examples. And we'll talk about this again at the end of the talk. So in general, asking for rationality is a bit too strong, and presently I don't know what's going on there. So as any mathematician does, when you can't answer some question, change the question to something that you can answer. So I'm going to weaken my question a little bit. And I'm going to replace rational with something weaker. So maybe like stably rational or retract rational or unirational or one of the many kinds of different notions of rational there are. But the weakest thing that I could hope for on the path to rationality is the existence of a K point. So my question now is, can the derived category be used to answer questions about the existence of K points? And that brings me to the theorem that I want to talk about today. That was joint work with Matt Ballard and myself. So it says that if X is a generalized Del Pezzo variety, which I will define shortly, then X has a K rational point if and only if its derived category admits a full etale exceptional collection, which again, I'll define that in a minute. And now is a good time to mention that in general, using the derived category to detect the existence of rational points doesn't work out too well. So a result due to Nick Addington, Ben Antio, Sarah Frey, and Katrina Honigs. Yeah, there's a result due to them, I guess this was in 2019, shows that there exist two derived equivalent varieties where one has a K point and the other one doesn't. So in general, the derived category is not great for detecting the existence of rational points. But in this very, very specific situation of generalized Del Pezzo varieties, we are able to extract some information about rational points. Okay, hopefully I've sufficiently motivated what I'm talking about here, because that ends the motivation section. And now I'd like to talk about the tools that I'm going to use. So one thing that I want to mention is like what's going on with derived categories of a variety over like a general field. So I just want to remind everyone what it means to have like full exceptional collection and what exceptional objects should be over an arbitrary field. So start off with a definition. I'm going to let A be a finite dimensional K algebra where X is a variety defined over K. And I'm going to assume that A has finite homological dimension. Okay, so an object E of the derived category is going to be called A exceptional if, so first of all, we need the endomorphism algebra of E inside of the derived category to be isomorphic to A. And we also want there to be no maps between E and shifts of E. Okay, so we'll call E just an exceptional object. If A is a division algebra over K. And we'll say that E is etale exceptional if A is a finite separable field extension of K, or an etale algebra over K. Okay, and I mean, I guess I should mention, if you're working over C, what you would expect, or what you should get, is if you have an exceptional object, the endomorphism algebra of that should be isomorphic to C. But actually requiring that for an arbitrary, like for a variety defined over an arbitrary field, is a little bit too restrictive. It's very restrictive to require that the exceptional objects have endomorphism algebras isomorphic to the base field. But I'll talk about that in a minute. Okay, so finally, if I have a totally ordered sequence of exceptional objects, we'll say this is a full exceptional collection. If each one of these E sub i's is A sub I exceptional, where A sub I is just the endomorphism algebra of E sub I. We also require that there are no maps between E sub I and shifts of E sub j when I is bigger than j. So there are no maps backwards in my sequence. And finally, we require that the collection generates the derived category as a triangulated category. Okay, so there's a few things I want to mention here. When I talk about etale exceptional, this is really, really exceptionally nice. So if I have a full etale exceptional collection, this means that the derived category can be decomposed as the derived categories of smooth points. So in some sense, that's like the nicest situation we could hope for, is that this derived category is generated by the derived categories of smooth points. If you're not familiar with the process of like finding full exceptional collections or semi-orthogonal decompositions, you are perhaps wondering which varieties have derived categories that decompose like this. So there are two results that are very relevant to what I'm talking about today. The first one is due to Matt Ballard, Alex Duncan, and Patrick McFaddin from 2017. And this theorem says that some variety x over k has a derived category that admits a full exceptional collection if and only if, when I base change to the separable closure, this new guy over the separable closure admits a full exceptional collection that is permuted by the action of the absolute Galois group. So how I've usually used this theorem is I'll start over the separable closure with a variety that I know has a full exceptional collection that's permuted by the absolute Galois group, and then I'll descend that to K. Also very relevant to what I'm talking about today is due to Kalamata. So I guess this is 2006 and 2013, which says that smooth projective toric varieties over a field K, where I require that K has characteristic 0 and K is algebraically closed, admit full exceptional collections. So in general, determining, like if you hand me an arbitrary variety and you're like, Alicia, does this derived category admit a full exceptional collection? I don't know the answer to that, and it's a non-trivial question. Okay, so that's all I have to say about derived categories for now. I guess I ought to say something about arithmetic toric varieties. So first of all, when I say a torus, so a torus over field K is an algebraic group T, such that when I base change to the separable closure, I get something that's isomorphic to GNM. And if T is isomorphic to GNM without base changing to the separable closure, we'll say that it's split. Okay, so to be precise about the definition of a toric variety, so a toric variety, which I'll call X, is just a variety, well, an algebraic variety that contains an algebraic torus as a dense open subset. In such a way that the action of T on itself, oh boy, extends to X. Okay, and what I mean by an arithmetic toric variety is just some variety over K so that when I base change up to the separable closure, I get a toric variety. Yeah, so such that the base change is an actual toric variety. Okay, so if you're interested in arithmetic toric varieties and aren't familiar with them, Alex Duncan has a paper on like twisted forms of toric varieties that really helped me when I was learning about this stuff. So I would suggest reading that. There's good news and bad news here though. The good news is arithmetic toric varieties are interesting. The bad news is that arithmetic toric varieties are interesting and that like weird stuff happens. So I want to give a few examples of that because some weird stuff can happen. And when I say weird, I mean unexpected, at least unexpected to me, who like as a graduate student learning about toric varieties was like, oh, this is so beautiful, this always works out. Arithmetic toric varieties are arguably just as beautiful, but behave a little bit more strangely. So I want to take a look at the projective real line. Okay, this is a toric variety. Well, an arithmetic toric variety. If I base change this up to C, I get P1C, which is a toric variety. If I want to view this as a toric variety, I need a torus. So when I'm staring at this, the obvious choice for me is R star. And R star is going to act via multiplication on the x coordinate. But it turns out this isn't the only choice of torus for P1R. I could also choose S1, and this is going to act on P1R via rotation matrices. Or complex multiplication, however you want to look at it. So these two choices of tori give me different actions on my toric variety. But when I base change up to C, R star is going to base change to C star, and S1 will also base change to C star because rotation matrices become diagonalizable over C. So when I base change, I no longer have a choice of tori. These things become the same thing. That's one weird thing that can happen. So usually we're going to need to make a choice of torus that we're working with. There's one more example that I want to take a look at. And that is, I want to look at P1R again. And I also want to look at the curve C, which is just the zero set of x squared plus y squared plus z squared sitting inside of P2R. Okay, so we've already seen that for P1R, there's two choices of tori. We could choose S1 or we could choose R star. It turns out, and you can check this, that for C, R star is not going to act appropriately on this. So S1 is the only tori that we can choose. Torus? Torus. But when I base change up to C, these things become isomorphic. Even though over R, these are vastly different varieties. One thing to notice is that C doesn't even have any R points. So they're definitely different over R. So I guess, what I want to say in general is that when you're working with arithmetic toric varieties, like my general process is to start with a toric variety over the separable closure. And then I'm going to base chain, well, descend, I guess, not base change. So I'm going to descend this to a subvariety, or a subfield of the separable closure to get some arithmetic toric variety Y with torus T. And then what I can do from there is I can twist by a T torsor. To get some other arithmetic toric variety X, which base changes to the same thing that Y does. Okay, so I think that's all I want to say about arithmetic toric varieties for now. But now I should probably tell you why I've been talking about arithmetic toric varieties. So first of all, in the result with Matthew Ballard, I talk about the existence of k-rational points for generalized Del Pezzo varieties. So this is what a generalized Del Pezzo variety is. I've written it as B sub 2n. It's a toric variety. Here are its rays. And the smallest guy in this family of toric varieties is the Del Pezzo surface of degree 6. Okay, please don't get mad at me. Generalized Del Pezzo variety is not a good name for these things. So DP6 is the only Del Pezzo variety that's in this family. But I would just think of these things as being really nice, symmetric toric varieties, at least over the separable closure, which, by the way, over the separable closure, this is where the fan makes sense. So I've drawn a picture of the fan of DP6 here. The fan no longer makes sense if I go to a subfield of the separable closure. Okay, so just to remind you, the theorem with Matthew Ballard said that a generalized Del Pezzo variety X has a K point if and only if its derived category admits a full etale exceptional collection. So now we know what a generalized Del Pezzo variety is. And I should also say that for forms of DP6, this was done by Mark Blanc in 2008.
Sorry,
Okay.
can I just ask about the definition? So are you saying a generalized Del Pezzo variety X is one that after base change to the separable closure has this description by rays?
Mm-hmm. Yep. Yeah, exactly. So to give you an idea of like what I was thinking for this theorem, like how to apply this theorem, I want to look at a quick example. So this isn't a generalized Del Pezzo variety, but as far as examples go, this is the easiest one to write down. So let's say I want to compare the derived category of P1C and the derived category of C, where C was this curve that was like the zero set of x squared plus y squared plus z squared sitting inside of P2. Okay, so we already know how P1 decomposes. It's just O and O of 1. And the endomorphism algebras of these guys, it's just a copy of C. You can check that the derived category of C is going to decompose as O and this guy F. And it doesn't even matter what F is. All that matters is what its endomorphism algebra is. So you can check that the endomorphism algebra of F is the Hamiltonian quaternions. So like the goal of this theorem is to like have this semi-orthogonal decomposition or full exceptional collection, and you stare at it, you look at the endomorphism algebras, and whether or not the endomorphism algebras are etale algebras over the base field determines whether or not your variety is rational or has a rational point. In this case, we only get a k point. Or I guess in the generalized Delpezzo variety case, we only get a k point. But in this case, in this particular example, I want to conclude that C is not rational because H is not a separable extension of the base field R. So okay. So there are a few important results that we use to prove this theorem that I want to talk really quickly about. The first is due to Kastrovet and Tevelev. From 2017. So this is not what their result says explicitly, but so it turns out that the derived category of these generalized Delpezzo varieties admits a full exceptional collection that is stable under the absolute Galois group action. So in this particular paper, they're looking at the derived categories of lows of mon and moduli spaces. And so these moduli spaces end up being like the toric varieties associated to the type A root system, and generalized Delpezzo varieties like as a family sort of sit inside of these. So okay, the other theorem that I want to mention is due to Klyachko and Voskresensky from 1984. And again, this isn't explicitly what their theorem says. I'm just adapting it to make sense in the context of the talk. So their theorem says that arithmetic toric varieties have a rational point whenever the T-torsor does. And further, a T-torsor has k points if and only if the T-torsor is trivial. So it's not actually a torsor, it's just the torus itself. So what this means in the context of this theorem is that our theorem basically boils down to figuring out if and when the derived category can see if a k form of these generalized Delpezzo varieties have been twisted by a torsor. And in this case, in this very specific particular case, that information is encoded in the endomorphism algebras of certain exceptional objects. Yeah, if you want to know more about the proof of this, I'm happy to talk about that. It's not in the archive yet, but it should be soon, pending me writing things down.
Excuse me.
Mhm.
I think your theorem on the Klyachko, it requires an arithmetic toric varieties to be smooth for this to be true, right?
I think so, yeah.
Yeah, I think if singular, then it's not necessarily true.
Yeah, I have no idea what happens in the singular case. Probably weird stuff. So yeah, I guess I should add smooth.
Thanks.
Thanks. Also, you might be wondering if a similar statement can be made for like general arithmetic toric varieties that I'm assuming smooth. And by this, I mean, is having a full etale exceptional collection strong enough to guarantee the existence of k rational points? I have an answer for you. It's no. So in the first paper that was joint work with Matt Ballard, Alex Duncan, myself, and Patrick McFaddin, we show and exhibit an example that there exists a smooth, geometrically irreducible threefold over Q with no Q points, whose derived category admits a full etale exceptional collection. And I've got a picture of it for you right here. So it turns out that it's very, very similar to these generalized Del Pezzo varieties. What I've drawn here is the fan for X of A3, where like this is just the toric variety associated to the root system A3. This particular picture might be of D3, but they're the same thing in this case. So yeah, I think that's all I have to say.
Okay. Thank you very much. Are there any questions, remarks?
Can you speak a bit more about this curve C as opposed to P1? So the example you gave, on the previous slide, there was an example for, yeah. So can you really make an argument like this, that can you see from the derived category that that C is not rational? How does that go?
Well, so I guess it's a little bit artificial, but like this is what I want to be happening with the generalized Del Pezzo varieties. Like if you give me a semi-orthogonal decomposition, I'm able to stare at the endomorphism algebras of the exceptional objects and determine whether or not the thing that you gave me was, well, in this case, had a K point. Does that make sense?
I mean, even as a narrative. So in this particular case, if someone tells you that I have a derived category with this decomposition, right? There's no way we can tell that it has no points, for example, right?
Yeah, yeah. And so this is like a really, really specific case.
So can I ask? So I mean, can you give a little bit of the idea of how you prove the direction that if it has such an etale exception collection that it has a K point? Because
yes.
Constructing exception collections, there are many ways to do that, but proving non-existence seems difficult in general.
Yeah. So for that direction, I use non-commutative motives as like a universal additive invariant. So it's like I have, okay, let's say you hand me a decomposition. Then when I hit it with non-commutative motives, this thing or sum of algebras, I guess, is going to be equivalent to like this guy here when I hit it with hit it with non-commutative motives. And so I guess basically you're just left with a sum of algebras, and these algebras are what tells you whether or not you have a K point. I don't know if that made sense.
So are you saying they admit a K point if and only if the non-commutative motive is a direct sum of non-commutative motives of etale algebras?
Yeah, yeah. And in fact, in this particular situation, there's only two algebras that need to be etale algebras. And these two algebras come from like, it's a little bit, I'm not sure if I can like explain it quickly, but these two algebras come from some short exact sequences that you get with, well, you get them for all toric varieties, but in this particular case, they work out really nicely.
Okay. If
can I ask a question?
Sure, of course.
Yes. What's the point about rationality for these varieties you call generalized del pezzo? When always, I mean, I guess having a k point is a necessary condition, and in dual examples I can made up, and they are sufficient, which are projective spaces and surfaces. But then I don't see higher dimensional.
I think I'm confused what the question is.
Sorry. What do you know about rationality, k rationality in this case? Can you state anything? Replacing x has a k point by x is k rational in some case?
Yes. So the first paper with Matt Ballard, Alex Duncan, and Patrick McFaddin and I, we show that we can replace this k point stuff with k rational if you know that you have a k point already and you have a full k exceptional collection, which is really restrictive.
Yeah, but I mean, for example, if your definition of generalized del pezzo variety for surfaces is just del pezzo of degree at most 6.
Yeah.
Sorry, and this is exactly the case where having a k point is equivalent to being rational. As soon as you get, at least dp5 is a special, but as soon as you get in degree smaller than 4, you have k points without being rational. So I was wondering whether this toric stuff has something to do. Like, for example, you start from Pn and then you have some toric blow up and blow downs, as you said in your weak factorization at the very beginning. Is there any relation to this? Maybe my question is confusing.
No. I think it's a good question. I just don't know how to answer it. So the problem is I don't know very much about del pezzo varieties. Like DP5, for example, I don't know very much about. But like DP6 is the only del pezzo variety that's in this family of generalized del pezzo varieties.
So you mean that, sorry. No, go on. I will ask you the question later. Sorry.
Oh, okay. But it's possible that this k point can be changed to k rational, but I'd have to look again at what I've written up.
So when you say that the DP6 is the only surface in this case, you don't have DP7 or DP8 or P1 cross P1 or even P2?
No.
Ah.
Nope.
Ah, okay. So it's a kind of the highest limit for toric blow-ups of Pn, right?
Yeah, so it's like, I guess if you take Pn, I'm gonna mess it up if I say it, but I've got the rays here for like a general del pezzo variety. Yeah, it's sort of like you take Pn and then you blow up a lot.
Okay, great. So I guess your theorem is true for everything that is intermediate.
Oh, like on the like
between Pn and the iterated blow up.
Mm-hmm.
Then you can start writing down exceptional collection and blowing them up and show. I don't know.
Well, so I think the problem is that, like, I have a full exceptional collection that's stable under the action of the absolute Galois group for these generalized del pezzo varieties, but I don't know that I necessarily have one for the intermediate steps.
I mean, if
like I'm not.
Yeah, the point is that.
Pardon?
Yeah. Okay. The intermediate steps.
Like I'm not sure that those exceptional collections will be stable under the absolute Galois group action off the top of my head.
in that case would mean that the action, I mean that you just blow up a point. For example, for DP6, you blow up a degree 3 point on P3 and there's nothing intermediate. But if you have like 3 closed points, anyway, maybe we can discuss this later separately, privately.
Yeah, sure.
Not to bore everyone. Thank
Actually, yeah, if you want, there is a discussion later actually at
Yes.
the Gather Town. So yes, and the link is indeed at in the chat. Yeah.